Hello and welcome to Solving Unusual Maths Problems, looking at calculus, curve sketching, differentiation and integration. To do some of the questions we're looking at today, we'll be using the shapes of curves we know to deduce the shape of more difficult curves, looking at curves which are defined implicitly, which means that y is not the subject of the formula, and considering graphs involving the modulus function and the modulus function itself, which you might not have met before. We'll also look at the behaviour around asymptotes, and we'll be using the fundamental theorem of calculus. Before we start any of the questions, I just wanted to recap on the shapes of curves like x cubed and any odd positive powers, as well as the even powers, x squared and x to the fourth. As we can see with x cubed, for large x, positive x, then y is also large and positive. But for large negative x, y is large and negative. But for the even positive powers like x squared and x to the fourth, for large positive and large negative x, y is large and positive, giving you that U shape. But for x to the fourth and x to the sixth, it might lump and bump around in between. And here we see the graphs of y equals 1 over x. And 1 over x squared. Both of these graphs have asymptotes, here along the x-axis and the y-axis in both cases. An asymptote, if you've never met the term before, is a line that the curve gets close to but never touches or crosses, except at that mythical infinity. Here we have the modulus function, or mod x. The symbol for it, these two vertical lines either side of x. Mod x is equal to x if x is positive or equal to 0, and mod x equals minus x if x is negative. So the modulus of 2 is 2. Modulus of minus 3 would be minus 3, which is 3. So it strips away the negative sign to give you just the value of the number. The modulus of minus a quarter would be a quarter. Graphically, mod x looks like this. When x is greater than or equal to 0, the graph of mod x is y equals x. When x is negative, the graph is y equals minus x, to give you this V shape. If you have to draw the modulus of any function, draw the original graph first, and then look at anything negative below the x-axis and reflect it in the x-axis to make it positive. As in this example here of y equals the modulus of x squared minus 1. Y equals x squared minus 1 would be a U-shaped curve going through 0 minus 1 on the y-axis. The modulus of that takes anything that's negative, the bits below the x-axis, and makes them positive. So this curve goes through 0 positive 1. And gives you that funny looking W shape you can see. So here's our first question to have a go at. We have 3 graphs and 3 equations to match up. We've already had a look at the basic shapes of graphs with the power of x to the 4 and x cubed. So that can help you identify the graphs if you look at what the overall power of the function is. And also we have repeated roots here. If you think of a quadratic curve with the equation y equals x plus 1 all squared, then you know that that means that touches the x-axis at the coordinate x equals minus 1. So pause the video here and have a go at matching up the equations to their graphs. So you can see here with the overall power in this first one being x to the power of 4, then it has to be that W looking shape. And it also ties in with the repeated roots at x equals 0 and x equals 2. Most definitely a quartic, or x to the power of 4. This equation here has an x cubed as the highest power of x. And it also has a repeated root at x equals 2 and another root at x equals 0. So we know it touches the x-axis when x is 2 and crosses the x-axis at 0, which means it looks like this. And finally we have x squared times x minus 2, another overall cubic, but this time the repeated root is at 0 and it crosses the x-axis when x equals 2. In this question we're going to draw the rational function 2x plus 1 over x minus 3. First of all, as instructed, we're going to make it into a plus b over x minus 3. And then we're going to use that rearrangement to help us draw the sketch of the graph in part B. Have a look in part B where there might be asymptotes. For example, when the denominator is 0. And then finally in part C, you're going to use our knowledge of the modulus function to sketch the graph of the modulus in part B. So pause the video now to have a go. So here we have the rearrangement of 2x plus 1 over x minus 3, which you could either do by algebraic long division, or you can do, as you can see here, by jiggling the plus 1 as minus 6 plus 7, which means if you then separate 2x minus 6 over x minus 3 and the 7 over x minus 3, taking 2 out as a common factor, you then have the x minus 3 dividing into itself to give you y equals 2 plus 7 over x minus 3. So we can use our knowledge of the general shape of the graph y equals 1 over x to help us do this function. If you look at what's happening to the graph of 1 over x and its transformations, you have the add 2 and you also have the 1 over x minus 3 effect, which I'm sure you remember with transformations means a shift of 3 towards the right. And also the times by 7, if you think of it as 7 times 1 over x minus 3, would just stretch it vertically. So altogether we have a shift of 3 to the right, which moves the asymptote, which is the y-axis, 3 to the right, and that also fits in with the idea of when x minus 3 equals 0, the denominator sees the graph go off to plus or minus infinity when x equals 3. With the add 2, this moves the whole graph vertically up to, and so you have the x-axis, the horizontal asymptote, is now moved to the line y equals 2. And it's been stretched as well vertically by the times 7. As you can see now, it crosses on the x and y axis, and we can find those coordinates by putting x equals 0 to see where it crosses the y-axis, and that gives you 0 minus a third. And to see where it crosses the x-axis, put in y equal to 0, which gives you the x value of -1/2. So you have the two coordinates where it crosses the axes. Now we have the final part of this sketch. It's the modulus of the function from part B. And as you can see, as we know from drawing modulus functions, anything in the curve which was in the negative y below the x-axis is now reflected in the x-axis and becomes positive. So there's the final sketch of the modulus of 2x plus 1 over x minus 3. So in this question we're looking again where equations of graphs and the curves match up, and one hint might be to have a look where those curves cross the axes. So pause the video now and have a go at this question. And as you can see here, when you put x equal to 0, which would identify where it crosses the y-axis, you get with this equation here y squared being -1, so no solutions. So this matches up to the graph which doesn't cross on the y-axis at all. When x is 0 in y squared equals x squared, we have the solution x is 0, y is 0, which matches up to this graph. And when x is 0 in y squared equals x squared plus 1, we get y squared equals 1, giving two coordinates which are 0 plus 1 and 0 minus 1. So it matches with this graph here. Let's have a look at question 12 next. So particularly when you get to part C, the least value of S, so that's when we can bring in some calculus. Because when you're looking for minimum values or maximum, come to that, dy by dx equals 0. In this case, probably ds by dx. So pause the video and have a go at number 12. So here we can see the solutions for part A, y in terms of x, and s is the sum of the two squares x squared plus y squared, which leads us to this expression for s. When it comes to part C, looking for the least value, if we differentiate with respect to x and put it equal to 0, we get a solution x equals 4, which when we substitute into s we get 32. Can we be happy that this is a minimum or least value? Well, d2s by dx squared, the second derivative, would be 4, which being a positive value implies that x equals 4 gives us a minimum. Having a look now at question 13, where BC is a tangent to the curve y equals x squared at the coordinate where x equals a. And we have to find the area of the shaded triangle in terms of a. So a bit of a hint here, it's a right angled triangle, and you could get the lengths hopefully of OC and OD. So pause the video and have a go at this question. So here you can see the sketch of y equals x squared, and we're about to find the equation of the tangent to the point B where x equals a. So y equals a squared. If we work out the gradient of x squared at any point, we get 2x. So at x equals a, we've got a gradient of 2a. So we can get the equation of this tangent, which is also the line BC and BD, and using the equation of a straight line, we end up with y equals 2ax minus a squared. D lies on the y-axis, so if we put x equals 0 into the equation of the tangent, we'll get y equals minus a squared, which also means then that the length of the line from O to D, the size of it, would be a squared. the coordinate C is on the equation of the tangent and crosses the x-axis. So if we put y equals 0 into the equation of the tangent, we get x equals a over 2. So that means that the length from O to C is of size a over 2. And O to C and O to D are the base and height of the triangle. So we have half base times height, which gives us an area of a cubed divided by 4. In this question, we're going to do the sketch of a modulus function of a modulus function. So if you build it up from the inside, as it were, and draw y equals 2x minus 1 and the modulus of that, etc., etc., and you should be able to identify then where the graph crosses the axes and the local maxima and minima. So pause the video and have a go at this question. So here we have the build-up of the graph in 3 stages. First of all, we have the modulus of 2x minus 1. And this can be seen by creating the straight line y equals 2x minus 1, which would cross the x-axis at a half, and then that reflection of that line in the x-axis. So the red line is y equals 2x minus 1. In the second stage, you can see where we have the transformation of minus 3, and this moves everything down 3, including the coordinate a half 0 now becomes a half minus 3, and this graph goes through the x-axis, and we can put y equals 0 to find out where it crosses. Because of the modulus, if we put the positive value of 2x minus 1, minus 3 equals 0, we get x equals 2, and also then the negative of the expression 2x minus 1 minus 3 equals 0 will give us another cross point when x equals minus 1, to give us these two coordinates here and here where the graph crosses on the x-axis. And then finally, stage 3, where we get the modulus of that function, then we can look at the points where it crosses the x-axis and have that reflection where the negative part of the graph reflects in the x-axis to produce the image we can see there of the graph. So in this question, we're going to draw f of x, which is x minus the integer value of x. And the integer value of x is the largest integer less than or equal to x. Here's one or two examples. So f of 3.7 would be 3.7 minus 3, 3 being the largest integer less than or equal to x, which gives 0.7. And f of 3 would be 3 minus 3, which is 0. So we're going to sketch the graph of y equals f of x as x goes from 0 to 4. And then after that, find the value of p for which the integral from 2 to p of this function is 0.18. So pause the video now while you have a go at this question. So here we have the sketch of f of x equals x minus the integer value of x, which is a series of 4 diagonal lines. In the second part, looking at where the integral from 2 to p gives us a value of 0.18. If we assume that p is some value obviously larger than 2, and then we can see we would have a right-angled isosceles triangle, the horizontal and verticals being equal length. So we can get an area as half base times height, and we get half p minus 2 all squared. By fixing that equal to 0.18 gives us values for p to be either 2.16 or p equals 1.4. As p is greater than 2 as it's the upper limit of the integral, p equals 2.6. In some of the following questions we'll be using the fundamental theorem of calculus, which you've already met and know, i.e. that integration and differentiation are the inverse of each other. In this question then we're looking at putting integrals in order of size without actually doing the calculations. I won't give any hints, so see how you get on. Pause the video and have a go. So without doing the calculations, you can use the areas to find out which one is the largest. And if we have a look at the y equals x between 0 and 1 and compare it to y equals x squared between 0 and 1, then the y equals x integral between 0 and 1 is larger. And between 1 and 2, the integral of y equals x isn't as large as the integral of x squared between 1 and 2. So by considering the area of the functions, then we have this order, that the smallest one is the x squared between 0 and 1, then x between 0 and 1, x between 1 and 2, and the largest is x squared integrated between 1 and 2. Here we have 6 graphs that we need to match up into pairs, and in each pair we have the function and its integral. Have a look at the shapes of the curves and see if you can relate that to the graph it represents, and have a so just recapping here the shape of x cubed and x to the power of 4, it looks like a is the cubic function and c is a quartic or x to the power of 4 function. So this would imply that c is the integral of a, and also that a is the gradient of c. If you integrate x to the 4th, as you know, you get 4x cubed. So that's one pair identified. A quick recap here of 1 over x or x to the minus 1 graph, and also x to the minus 2 or 1 over x squared graph. And we can see that E graph looks like x to the minus 1, and D looks like an x to the minus 2, but it's negative. Being that reflection in the x-axis, it's minus x to the minus 2. And if you look back at the gradient of E, they're always negative, so this would imply that D should be minus x to the minus 2, and it is the differential of E. So if D is the differential of E, then E is the integral of D. So that's another pair identified. This leaves the last pair, F and B graphs, and again we can see that F looks like x to the minus 1 with B a positive x to the minus 2. And if we look at the gradient of F, we can see it is indeed positive. So this implies that B is the gradient or the differential of F, and therefore F would be the integral of B. Here's another question linking area and integration. And if we look at the equation of the curve y equals x plus a times x minus b all squared, we can recognise again the repeated roots there with the power of 2. So we can work out where that curve crosses the x-axis before we start to integrate. So pause the video and have a go at this question. So you can see from the repeated root, this implies that the point where the curve just touches the x-axis would be B, and where the curve crosses the x-axis would be minus a, when you put y equal to 0. So we know what our limits are for the integral, So now we need to expand and see what the polynomial is that we will be integrating to give the expression there at the bottom. So here's all the working out. You've just got to be very careful with your algebra. And when you've integrated, it would look like this. Putting in your top limit of b and your lower limit of minus a gives these expressions. And then expanding out and subtracting the result of the lower limit. At this point it's easiest to take out the 12th as the common factor because of all the fractions, which gives you then whole numbers that you can deal with. And finally, with the 12th as the common factor, it boils down to b to the 4th plus a to the 4th plus 4ab cubed plus 4a cubed b plus 6a squared b squared, which I hope you recognise is a plus b to the power of 4 from the binomial theorem expansion. So we end up with the integral being 1/12 a plus b to the 4. In this question we've got the integration from 0 to 4 of a modulus function x times x minus 2. And the first thing we have to do is to show that that's equivalent to the integral of x times 2 minus x between 0 and 2, and then that's added to the integral of x times x minus 2 between 2 and 4. The best way to show this would be to draw the graph of the modulus function x times x minus 2, and as we've seen already that we need to do that firstly by drawing just x times x minus 2, which is a quadratic, and that's my hint for you to start off with. And then when you've drawn x times x minus 2, then have a look at the graph of the modulus of that function. So pause the video now and have a go at this question. So now you can see we've got the graph of y equals x times x minus 2. If you put y equal to 0 to see where it crosses the x-axis, you get the roots x equals 0 and x equals 2. It's a quadratic and it's positive, so it's a U shape. So by symmetry you can see it has its minimum when x is 1, halfway between 0 and 2, and if you put 1 in as x into the equation you get minus 1. So it's got its minimum point at 1 minus 1. Then below it we have the modulus of x times x minus 2, where, as we talked before, this means that everything that was negative would then be reflected, if you like, on the x-axis, and so becomes positive. So if we're going to integrate the modulus of x times x minus 2 between 0 and 4, then we need to look at it in two separate functions, because between 2 and 4 we have the original y equals x times x minus 2. However, between 0 and 2 we have the shape of minus x times x minus 2, which you can write then as minus x squared plus 2x, or factorise as x times 2 minus x. So this can help us work out what the integration should be. So to finish off the actual integration, now we've seen from the graphs that we have to integrate the functions separately between 0 and 2, where we're integrating x times 2 minus x, and then between 2 and 4 x times x minus 2, we can just go ahead and integrate. So multiplying out the brackets here to give us 2x minus x squared, and here we have x times x minus 2 in the second integral, integrating and then putting in the limits, top limit, bottom limit, and subtracting, and the same with the second integral, and eventually I hope you got the same answer as me, 8 square units. In this next question from the Enrich website, we are looking for the final thing we need to calculate is what's the integral of f of x between 0 and 1, and show that that's less than or equal to 1. We are told that f of x divided by x is less than or equal to 2 when x is between 0 and up to 1, including 1. X is greater than 0 as it says that f of 0 is 0. So I would start this one off by making f of x the subject of the formula, and then as we are looking for the integral of f of x integrated between 0 and 1, then doing that to both sides of that integral. Pause the video and have a go at this question. So given the conditions at the start, that f of x 0 was 0, and as long as x was greater than 0 and less than or equal to 1, f of x divided by x was less than or equal to 2, we're required to show the integral between 0 and 1 of f of x is less than or equal to 1. If we take f of x divided by x is less than or equal to 2 and multiply both sides by x, and x can't be 0 because that was not in the domain given for x, we could then integrate both sides of this inequality between 0 and 1. On the right hand side we then have the integral of 2x, which is x squared between 0 and 1, and we get the 1, and we've shown what was required in the question. So in this step question we are given the curve's equation. A is a real number, and we have to show that for any value of a, that curve touches the curve with the equation y equals x cubed at 2, 8. And here touches at a point B means that the curves meet at B and have the same gradient at B. We've got to find the coordinates of any other point of intersection of the two curves. So we're looking here at two things: where the curves meet, where the curves are equal, and where the curves have the same gradient. So pause the video and have a go. If we know that the two curves have the same gradient, then we can use differentiation to find their general gradients and put in the coordinate 2, 8, where x is 2, to work out the gradient at that point. So here's the gradient of the first curve. When x is 2, we get dy by dx, the gradient, to be equal 12. And also in the other curve, y equals x cubed, the general gradient dy by dx is 3x squared, and when x is 2, the gradient is 12. So at the coordinate 2, 8, the curves have the same gradient, i.e. they touch. Now the points of intersection, we could put the curves equal to each other because we know that they are both y equals equations, and if we do that then we can solve where they cross. So arranging that equation equal to 0, bringing the x cubed over the other side, we now have a cubic equation that we can say is equivalent to x minus 2 all squared times bx plus c. The reason for that is we are told that the curves touch when x equals 2. So then this is a repeated root of this equation. So the cubic we have found by putting the curves equal to each other must be equivalent to x minus 2 all squared times something x plus a constant. So if we use b and c to represent the constants, we can now compare both sides of the equals and see that the number of x cubes would be a minus 1 on the left hand side, and equal to bx cubed if we expanded these two brackets. You can see that by inspection. So we have an equation linking a and b. If we put b now in as a minus 1, and if we compare the constants, so we have a minus 1x cubed, so many x squared, so many x, and we have negative bracket 8a plus 16 as the constant term on the left hand side. And we have a look at how many constants we have on the right hand side here. We would get constants from the minus 2 all squared, which is positive 4, times c. So it's equal to 4c on the right hand side. And simplifying that, we get that there's a relationship between a and c, that c equals minus 2a minus 4. So now substituting in that b is a minus 1 and c was minus 2a minus 4, so pulling the minus sign out there as a common factor. We know these curves cross when x minus 2 all squared equals 0, but we know that x equals 2 is where they touch, or when the other bracket is equal to 0. So if we put this bracket equal to 0 and make x the subject of the formula, we get that x equals 2a plus 4 divided by a minus 1. So as long as a does not equal 1, then we can have an expression for the x coordinate of the points, any other points where the curves cross. Here's another enriched question, this one on integration. Which of the following two expressions is the larger, p or q? So pause the video and have a go at this one, and just use the usual rules of integration. So integrate x to a power, then you always add 1 to the power and divide by that new power. A and b are positive, so we don't have to worry about there being the powers of x to the power of minus 1. So when you integrate x to the power of a plus b, you add 1 to the power and divide by this new power, and then you put in your limits t and 0 to give you this expression here. Similarly for q, when you're integrating x to the power of 2a, you'll get x to the power of 2a plus 1 divided by that new power, and you're about to put in your limits t and 0, and similarly for x to the power of 2b. You'll then need to multiply these two.
So, when you look at the expression for q, now that you've multiplied them, you should end up with the expression that we've got here at the top. And now we need to look at the comparison of p and q. How can we decide which one is larger? Q with a denominator of 4ab plus 2a plus 2b plus 1, or p with this denominator. They're both quite similar, and they have 2ab plus 2a plus 2b plus 1 in common, though p has an extra a squared plus b squared, and q has an extra 2ab. So which one of those is larger? Is a squared plus b squared larger than 2ab? Well, if we subtract 2ab from both sides, we see that we could get the expansion of a minus b all squared, which is positive, or 0 if a equals b. So working out backwards gives us the idea that a squared plus b squared is greater than 2ab when a does not equal b. So it means that p does have the larger denominator when a is not equal to b, which means that p is less than q, or if a equals b, then p is equal to q. So generally, q is larger than p, except when a equals b, and then p and q are the same size.
So that's the end of the questions involving this topic of curve sketching, differentiation and integration. I hope you've enjoyed doing them.